Welcome back. And in this video, we're going to be looking at enthalpy level diagrams and using those to calculate Bourne-Haber cycles. So we're on page 7 of your notes, and this is the enthalpy level diagram for sodium chloride. And you'll notice it's exactly the same as the ones you've done in the energetics notes, but just with a few more lines. So just to remind you, anything going up the page, that is an endothermic reaction, because the delta H will be positive as it is here and here. Anything going down is going to be an exothermic enthalpy change. Notice the negative signs here and here. So we start with the elements in their standard states, and I remind you they have an enthalpy of 0. So this is what we call the datum line. Then as we go up the page, first of all we have this enthalpy of atomization, and this is of sodium, and we're turning it from a sodium solid into sodium gas. Next, going up again, this is the first ionization energy of sodium. Notice we need to turn it into a gas first, so this is delta H IE, and this is the first ionization energy of sodium gaseous, and you'll notice we've now got an electron here. Last but not least, we need to remember to atomize our chlorine. So this is delta H atomization of our chlorine, half Cl2. Notice the square brackets, and it's half Cl2 gaseous because we're turning the element into gaseous atoms. Coming down this side, I first of all have the electron affinity of chlorine. So there's delta H Ea again of chlorine. Notice the square brackets there. I should put square brackets around this one as well. On the bottom half of the page, we have the solid and the gas, the elements going to the compound. So there's delta H formation of sodium chloride, solid. And we can also take the gaseous ions and turn them into the lattice, and that would be delta H lattice, again of sodium chloride solid. And we've constructed our Bourne-Haber cycle. We can then use this to calculate the lattice enthalpy of sodium chloride in exactly the same way that we did before, knowing that delta H formation is equal to the sum of everything else. So what I'd like you to do now is pause the video and have a go at the next two examples on pages 8 and 9. So as before, we're going to start with the datum line. We've got the data at the top of the table, and we're going to construct our Bourne-Haber cycle, this time for potassium iodide. So I'm going to start quite low down on the page because I want to draw my datum line. So that is my line at 0. And those will be my elements, in this case potassium and half an iodine. And iodine is a solid at room temperature and pressure. And I'm going to turn those, first of all. This bit, it doesn't matter which order I do the atomization in. I need to do both the atomization of potassium and of iodine, but I'm going to do potassium first of all. So I'm going to turn potassium into a gas, and I'm going to leave my iodine alone. And then I'm going to take another line going up, and I'm going to notice this doesn't necessarily have to be drawn to scale. I'm going to now do my ionization of potassium, and I've kicked out an electron. I'm going to put it there because it just helps me to remember I've got to add it back in later on. Now I have to atomize my iodine. I'm going to turn that, and I've now got my potassium, gaseous ions, and my electron, and I've now got my iodine, gaseous. So far all these reactions have been endothermic, but now I'm doing the electron affinity of iodine, and if you notice from the data, iodine is a negative value, so I need to come down the page because it is an exothermic reaction. And I'm going to go to potassium gaseous, and iodine has now become iodide. That electron has been transferred onto that iodine. Now I have both my gaseous ions and my elements, and I can use both of those to form my solid potassium iodide, either using enthalpy of formation or lattice. Now what I can do is go around and put the data or the symbols on, and I'm going to do both. So this is my delta H formation of potassium iodide. This is my delta H lattice of potassium iodide. Again, that's a solid. Going from here to here, that's the delta H atomization of potassium. And here is the delta H ionization energy 1 of potassium. Here I have the delta H atomization of half an iodine solid, and here I have delta H EA 1, so the first electron affinity of iodine. Gaseous, and I've got my lattice there. I can also put in my numbers, so the enthalpy of formation is going to be minus 411. The delta H atomization of potassium is plus 90. Ionization plus 418. Atomization of my iodine plus 107. The electron affinity of my iodine minus 314. I'm going to use these to calculate my delta H lat, so that I know that my delta H formation is equal to the sum of everything else. Because if you follow the arrows round, enthalpy formation is equal to all these other enthalpy changes. So I've got my enthalpy of formation, minus 411, equals my delta H lattice plus all the other enthalpy changes. So that's plus 90, plus 418, plus 107, and minus 314. And if I put all those numbers in my calculator and solve it correctly, I should get delta H lattice equaling minus 712 kilojoules per mole. So the enthalpy of lattice of potassium iodide is 712 kilojoules per mole. That's how much energy it releases when we form 1 mole of it from its gaseous ions. Next, we're going to have a go at drawing the Bourne-Haber cycle for calcium oxide. Again, I'm going to start with my datum line relatively low down on a piece of paper, because I'm going to start with calcium, solid, and oxygen. And again, I need half an O2 gaseous molecule, or moles of molecules. First thing I'm going to do is I'm going to atomize my calcium, because I'm going to get Ca gaseous, and again leave the oxygen alone for the moment. And then I'm going to take that, and I'm going to do my first ionization energy of calcium. So I get Ca plus. I've lost 1 electron, still got my half O2 gas there. Then I'm going to do my second ionization energy of calcium. Now I've got Ca2 plus this now 2 electrons, plus still my half O2 gas. That should be gas there as well. Now I'm going to atomize my oxygen, turn my oxygens into gaseous atoms. So I've got my Ca2 plus gaseous, plus my 2 electrons that I've removed, plus now I've got O gaseous because I've atomized my oxygen. Now I'm going to do the first electron affinity of oxygen, which is negative, so it's going down the page. And I have still got my Ca2 plus, and I've done the first electron affinity, so I've added 1 electron to my oxygen. Now I'm going to do the second electron affinity, the second electron affinity, and now I'm trying to add an electron to an already negatively charged ion, and unsurprisingly, that will be endothermic. That's why I'm going back up the page. And now I've got my Ca2+ gaseouses and my O2- gaseous. So I've got my elements and I've got my compounds, so my ions, and now I can join them together and complete the cycle by making calcium oxide solid. So I can use my enthalpy formation to do that, or extending this line a little bit further, I can use my gaseous ions to do that. And again, I have my Bourne-Haber cycle. What I've done now is put on which enthalpy changes we've got. So we've got the atomization of calcium, the first and the second ionization energies of calcium, the atomization of oxygen, the first electron affinity of oxygen, second electron affinity of oxygen, the lattice enthalpy, and the enthalpy of formation. So I've now done exactly the same as I did before. In other words, I've got enthalpy formation is equal to the sum of all the other enthalpy changes. So the enthalpy of formation of calcium oxide is minus 635.1, and that equals my delta H lattice plus 2819.3. So my delta H lattice is equal to minus 3454.4 kilojoules per mole. And as you'd expect, given the fact that it's a 2+ ion and 2- ion, it's got a significantly higher delta H lattice than the potassium iodide example. Potassium iodide, the ions are much larger and they have a lower charge. Hence, their delta H lattice is much less exothermic. So in the next 2 pages, there are some examples of students' responses to completing Bourne-Haber cycles. There are 3 students' answers. Go through them, see how many marks out of 3 you would give for each answer. So this student was given 1 out of the 3 marks. What they've forgotten to do is they've forgotten to times by 2 here and here, because you've got 2 moles of bromine being atomized and you've got 2 moles of bromine undergoing electron affinity. So you're adding 2 moles of electrons to 2 moles of bromine gaseous atoms. You've also forgotten the state symbols here, and that's dropped the 2nd mark. So that's 1 out of the 3 marks. Again, on the calculations here, they've forgotten to times, again, the electron affinity of bromine by 2, because there's 2 moles of bromine atoms, and they've forgotten to divide the answer by 2 at the end, because we want the single electron affinity of bromine, not 2 times the electron affinity of bromine. The next one was given full marks. They have all the state symbols and all the labelling correct. The last student's answers was very confused. They started putting equations in the boxes rather than the formula of the species. Again, they've forgotten to times these answers by 2, and quite often in some of the boxes we're even missing bromine. They did get the ionization energies correct, so you got 1 out of 3.